Hello all. Today I will solve an example about a vapor compression refrigeration cycle. So just to remind you what is a vapor compression refrigeration cycle. So the system consists of again two heat exchangers. One is condenser, the other one is evaporator. And in between we have a compressor for the cycle and an expansion valve. So what we have here, actually a refrigeration cycle. So we start at state 1. Generally it is a saturated vapor or superheated vapor. So in this compressor we require external work in order to increase the temperature and the pressure of the working fluid. And it comes to the condenser at state 2. So heat is rejected here. This is Q dot out, and this is state 3. So this is the expansion valve, and we have state 4 here. Then this is where the useful heat transfer is performed. So actually this is nothing but an equivalent to we have a high temperature reservoir, a low temperature reservoir, a system working as a cycle, now carrying energy in the form of heat from low temperature reservoir to high temperature reservoir. Of course, in order to perform that, we require work. So this is a QC, and this is this is Q dot H, Q dot H, and this is Q dot C cold. So this is an equivalent system, of course. In order to carry the energy from low temperature to high temperature, we require work input, and this is in the form of the work. And here our performance criteria for the system coefficient of performance. Desired output is, this is the refrigerator space where you want to cool it. So desired output is how much energy you are removing from this refrigerated space, and in order to do that, how much work you need. This coefficient of performance is generally greater than 1. So this is an equivalent system here, and if we follow it, okay, this is a compressor and the condenser. You can think of the condenser here as the uh, the tubing at the back of your refrigerator, which is hot. So in order to remove energy, so to the surrounding. And then expansion valve drops the pressure to high pressure, compressor pressure to the evaporator pressure. Uh, Now, if you look at the TS diagram of the system, we can see this is the two-phase system. So we start from, we have actually two pressures, constant pressures. So this is the TS diagram. And we have also this constant pressure line. And if this is the saturated vapor, this is state 1. So of course, we go to 2S, and then we go to 3 here, and constant throttling process is an expansion of constant enthalpy process. Okay, so we have two constant pressures here. One is the compressor exit pressure and the evaporator pressure. Now, generally, you need a special working fluid here, working fluid for these systems is special, and depending on your application, how much you want to cool the refrigerator space, we use different refrigerants. Ammonia is an example of those, and different types of refrigerants are also examples. So in an example here, what we perform, we have the working fluid. The working fluid is ammonia, and we know the data at various points. So the ammonia exits the evaporator as saturated vapor at minus 22 degrees Celsius. So this temperature, so here this is state 1, and this is minus 22 degrees Celsius, and the refrigerant enters the condenser at 16 bar. So this pressure is 16 bar, and 160 degrees Celsius. Okay, so we have another 160 degrees Celsius here. So 16 bar. So there's no significant heat transfer between the compressor and its surroundings, and the refrigerant passes through the evaporator with a negligible change in pressure. So we neglect the pressure drops in both condenser and the evaporator. So we have here T1 is minus 22 degrees Celsius, and T2 is 160 degrees Celsius, and Q in is equal to 150 kilowatts. Okay, so this is the refrigerating capacity. Refrigeration capacity is 150 kilowatts. Okay, so what is required for this to happen? We need what is the mass flow rate of refrigerant, and what is the power input to the compressor, and part C, what is the coefficient of performance, and part D, the isentropic efficiency of the compressor. So that's why I showed the 160 degrees here. So this is state actually 2, but state 2s is going to be at lower temperature. So now let's look at the states, fix each principal state. So when you look at state 1, what we see here, what do we know? T1 is equal to minus 22 degrees Celsius, and it is saturated vapor given in the statement of the problem. So this state is fixed for, we can look for the ammonia table, and H1 is kilojoule per kilogram, and entropy is kilojoule per kilogram Kelvin. So when we look at the state 2, what we know about state 2, we know the temperature and we know the pressure. So state 2 is also fixed. P2 is 16 bar, and T2 is 160 degrees Celsius. So from here, H2 is looked up in the tables. And for state 3, what do we know? If we go back, state 3, okay, we know the pressure, 16 bar, and we know that it is saturated liquid. So P3 is 16 bar, and it is saturated liquid. So it is given in the statement of the problem, saturated liquid. So H3 is 376.46 kilojoule per kilogram. So when we come to state 4, what do we know about state 4? So this is the temperature we know, minus 22 degrees Celsius. And what else? We know that H3 is equal to H4 because of throttling process. So that's major information. Throttling process, and H4 is equal to H3, which is equal to 376.46 kilojoule per kilogram. So what is the mass flow rate? Part A, mass flow rate. We calculate mass flow rate with the hint of refrigerating capacity. So use the refrigerating capacity. And what is that? What is that in terms of refrigerating capacity? Q dot in here. Okay, so this is Q dot in, which is 150 kilowatt. Is flow rate is same everywhere, and it is H1 minus H4. H1 minus H4. So here we can easily determine 150 kilowatt, 14, 15, 08 minus 46. So the units are suitable. We don't need to apply any factors. 1444 kilogram per second. So this is an answer for part A. So part B, we are required to calculate the power input to the compressor. So the compressor power, of course, with that compressor m dots, by knowing this information, H2 minus H1 is easily here, H2 minus H1. So this is going to be equal to 0.1444 kilogram per second. And this also that doesn't require any conversion, and it's 55.4 kilowatts. So compare it with the 150 kilowatt of refrigerating capacity. In order to calculate this, in order to obtain this capacity, you need 55.36 kilowatt input to the system. So coefficient performance is very obvious. Desired output, we want to refrigerate, but in return, we want to give some power to the compressor. So this is, as I said, coefficient of performance greater than 1. It is also better. And for the part D, we would like to obtain isentropic efficiency. You know that for the compressor, H2S minus H1, H2 minus H1. So here we know H2, okay? So we know H2, and H2 is here. So this is the actual graph, non-isentropic 1 to 2, but 1 to 2s is isentropic, which means that S2 is equal to S1. Okay, so we can determine that state. And from here, what we can calculate by determining 125 5.38 minus weight, which is 0.888, and it is 88.8%. So this is the part B. Okay, and in the next example, we're gonna see a heat pump.